Good morning to all. First of all, I would like to thank for the given opportunity in front of you. Now I am going to present the subject atomic and molecular spectroscopy presented by Dr. K. Dhanabalan. Introductions. First, we come to understand the difference between atomic spectra, molecular spectra and atomic and molecular spectroscopy. First one, atomic spectra. The range of characteristic frequencies of electromagnetic radiations that are readily absorbed and emitted by an atom. The atomic spectrum is an effect of the quantized orbits of electrons around the atom. An electron can jump from one fixed orbital to another. If the orbital is jumps to has a higher energy, the electron must absorb a photon of a certain frequency. If it is of a lower energy, it must give off a photon of a certain frequency. The frequency depends on the difference in energy between the orbitals. Explaining this phenomenon was crucial to the development of quantum mechanics. The atomic spectrum of each chemical element is unique and is largely responsible for the color of matter. Atomic spectra can also be analyzed to determine the composition of objects such as stars that are far away. Next one, molecular spectra. The optical emission and absorption spectra as well as Raman scattering spectra that belong to free or weakly bound molecules. Molecular spectra have a complex structure. Typical molecular spectra are band spectra which are observed in emission, absorption and Raman scattering in the form of the aggregate of more or less narrow band in the ultraviolet, visible and near infrared regions, and break down into a set of a closely positioned lines when the spectral instruments used have sufficient resolving power. The specific structure of molecular spectra differs for different molecules and generally speaking grows more complex as the number of atoms in the molecule increases. Last one, atomic and molecular spectroscopy. That means both in its basic and in its applied aspects, it is a dynamic state of development. It continues to provide new fascinating possibilities for a deeper understanding of the fundamental properties of the building blocks of matter and their interaction with electromagnetic radiation. It generates new possibilities for practical applications in industry, chemistry, astronomy, geoscience, biology, medicine and information technology. Next topic, quantum spectra of electron in atoms. Actually, we know the structure of atoms. We come to electron states. Here, 4 types are classified. Principal of quantum number n, orbital quantum number L, magnetic quantum number ml, magnetic spin quantum number ms. Before discussing this 4 points, we come to some information about that atomic structure. That means electrons are surrounded the nucleus in an atom occupying different orbitals. The Heisenberg conservative principle states that the moment the position of the electrons cannot specified previously. That means delta x delta px greater than or equal to h by 2 pi. Each electron orbital is called quantum state, which a set of quantum numbers classified n, l, ml and ms. The characteristics of the quantum numbers are summarized below. That means here discussed 4 points. First one, principal of quantum number. Second one, orbital quantum number. Third one, magnetic orbital quantum number. Fourth one, magnetic spin quantum numbers. Now we are going to discuss the first one, principle of quantum number. Here n is called the principle of quantum number. The serial number of the cells starting from the innermost is designed as its principle of quantum number n. It can take only the integral values excluding 0, n equal to 1, 2, 3, 4, etc. Second one, orbital quantum number L. Here L is called that orbital quantum number. It is related to the shape of the electron orbital. Here L is called the orbital quantum number. L is related to the shape of the electron orbital. L can take that integral values from L equal to 0 to L equal to minus 1. That means here if n equal to 1, L equal to 0, n equal to 2, L equal to 0, 1, n equal to 3, L equal to 0, 1, 2. The values of L defines suborbitals which are denoted by the certain letters L equal to 0, 1, 2, 3, 4 corresponding to the notations S, P, D, F, G. Next one, magnetic orbital quantum number ML. Here ML is called the magnetic orbital quantum number and defines the spatial quantization of the electron probability density. ML can have that values minus L, minus L plus 1, minus L plus 2, etc. minus 1, 0, 1, etc. L minus 2, L minus 1, L. So that there are 2L plus 1 values of ML. Next one, magnetic spin quantum number ms. Here ms is called that magnetic spin quantum number. It defines the spin of the electrons. There are two possible states of the spin. One is that spin up, another one is spin down. This is the corresponding values of ms equal to plus 1 by 2 and minus 1 by 2. Next one, continued from that spin, Pauli's exclusion principles. That means the Pauli's exclusion principle states that no two electrons can have that same set of quantum numbers. In other words, only one electron can occupy a given quantum state. When there are a number of electrons surrounding the nucleus of an atom, they have to occupy different quantum states. The order of the increasing energy of the orbitals is as follows. Here given the table. In the box mentioned that location of electrons settled in each orbitals. Okay. Next one, the digit values of the principal quantum number n. Following letters denotes the suborbitals corresponding to different values of L. An electron can be excited from a lower energy state to higher energy state by the supply of energy from an external source. When there is such electronic transitions from one level to another, electromagnetic radiation of a specific frequency wavelength observed or emitted. If energy is observed, the electron is excited to a higher energy level. Energy is emitted if the electron falling to a lower energy level from a higher energy level. The energy difference delta E between the two states is related through the Einstein relationship to the frequency nu of the radiation emitted or observed. That is here presented delta E equal to h nu. Similarly, we can relate the frequency of the radiation to its wavelength lambda, the velocity of light c. That means c equal to nu lambda. Now this topic over. This topic discussed 4 points: principle of quantum number n, orbital quantum number L, magnetic orbital quantum number ml, and magnetic spin quantum number ms. Everything discussed this topic. Thank you.